4 years have passed since that unforgettable Christmas day in 2021, when humanity watched with collective anticipation as the most sophisticated telescope ever constructed ascended from French Guiana into the endless expanse above. 3 decades of development, $10 billion invested, and innumerable restless nights from thousands of brilliant minds across the globe culminated in that singular, breathtaking moment. The James Webb Space Telescope embarked upon its odyssey to transform everything we thought we understood about our cosmic home. If these tranquil explorations of astronomical discovery bring you peace, I would deeply appreciate your subscription and a tap on that notification bell. This evening, we venture forth on an expedition through the most revolutionary celestial findings of our era. Feel welcome to relax your eyes, draw a calming breath, and allow your thoughts to drift across the vast reaches of space as we examine what this extraordinary instrument has unveiled about our galactic surroundings and the regions beyond. I would also cherish knowing your current location on our small planet. Share your time zone and whereabouts in the comments below. There exists something profoundly moving about pondering these cosmic truths while dispersed across our tiny blue marble, each of us beneath the identical ancient heavens that Webb now helps us comprehend in unprecedented ways. Welcome to Dark Cosmos Theory. Let us commence our journey. Here is what renders Webb's narrative genuinely exceptional. This represents far more than simply another orbital observatory equipped with superior mirrors and enhanced imaging capabilities. This stands as humanity's first transparent portal into the cosmic genesis itself, a temporal device, capable of observing backward across 13 billion years to witness our universe during its infancy, still radiating with the luminescence of creation's aftermath. Welcome to this exploration through one of the most extraordinary periods in astronomical history. We shall investigate how an observatory circling in darkness, 1 million miles distant from our world, has already transformed textbooks, confronted established theories, and unveiled our perception to cosmic occurrences we never realized existed. The findings we are preparing to examine transcend mere impressive scientific accomplishments. They constitute revelations that alter our comprehension of humanity's position in the magnificent cosmic narrative. Our tale commences with something potentially unexpected. Webb does not circle our planet like its forerunner, the Hubble Space Telescope. Rather, it travels to a unique location in space, designated Lagrange Point 2, where the gravitational influences of Earth and our Sun generate a stable position 1 million miles from home. Here, protected by a tennis court-sized solar shield, offering protection equivalent to SPF 1 million, Webb hovers in constant darkness, its instruments chilled to temperatures more frigid than Pluto's surface. This is not merely engineering for engineering's purpose. Every element of Webb's construction serves a significant function. You understand, our universe undergoes expansion. As illumination journeys across billions of years of cosmic chronology, it becomes elongated like elastic being stretched. The visible radiation from the most primordial stars and galaxies has stretched so extensively that it now exists as infrared emissions, invisible to human perception but perfectly detectable by Webb's groundbreaking instruments. This signifies that when Webb examines deep space, it literally observes backward through time. The farther it investigates, the younger the universe becomes. It resembles possessing a cosmic archaeological implement that can excavate layers of cosmic chronology, exposing secrets concealed for longer than Earth's existence. Yet even the most hopeful astronomers were unprepared for what Webb would genuinely discover. Within mere months of commencing scientific operations in July 2022, this extraordinary machine began transmitting imagery and information that rendered the scientific establishment astonished, energized, and considerably puzzled. The initial shock arrived from the deepest expanses of space and time. In May 2024, Webb identified something that should not exist according to our finest comprehension of cosmic development. A galaxy, labeled JADESGSZ 140, illuminating brilliantly in the cosmic darkness, merely 290 million years following the Big Bang. To establish perspective, if the complete chronology of our universe compressed into 1 year, this galaxy would have materialized by January 8th. This finding signifies considerably more than merely a new distance record for the most remote galaxy ever detected. It constitutes a fundamental challenge to everything we presume to know about how rapidly the universe could organize itself following the cosmic spectacle of creation. According to our theoretical frameworks, galaxies, this enormous and luminous, simply should not have possessed sufficient time to develop so early in cosmic chronology. Peter van Dokkum from Yale University, among the scientists participating in this discovery, expressed the significance perfectly when he informed reporters that this currently represents the most distant object recognized to humanity. Yet, more significantly, he emphasized that Webb was not anticipated to locate any galaxies this early in cosmic chronology, at minimum not during this mission phase. The implications prove staggering, if enormous. Mature galaxies could materialize this rapidly following the Big Bang. It indicates that the infant universe was considerably more active, considerably more efficient at constructing complexity than we ever conceived. It resembles discovering that not only could ancient civilizations construct magnificent metropolises, but they were accomplishing it more rapidly and efficiently than modern societies possessing all our sophisticated technology. Yet this remote galaxy was not solitary. Webb has uncovered an entire population of surprisingly massive galaxies in the primordial universe, some as enormous as our Milky Way, formed within merely the first 700 million years of cosmic existence. These cosmic titans challenge our fundamental frameworks of galaxy development and compel us to reconsider how rapidly matter could aggregate together under gravity's patient influence. The enigma intensifies when we examine the chemical makeup of these ancient galaxies. Webb's spectroscopic abilities allow it to analyze the illumination from these distant objects like a cosmic laboratory, decomposing their starlight into component wavelengths that expose the elements present in their cosmic stars. What it discovered proved completely unexpected. These primordial galaxies contain remarkably elevated amounts of nitrogen compared to what we observe in our Sun and local stellar vicinity. Meanwhile, most other heavy elements are present in considerably lower quantities than our models anticipate. This indicates that stellar development, the mechanism by which stars forge heavy elements in their cores and disperse them through supernova detonations, was functioning under vastly different conditions in the infant universe. It resembles discovering that ancient metallurgists were somehow manufacturing advanced alloys, utilizing techniques we do not comprehend, generating compositions that our modern grasp of chemistry declares should not be feasible. These discoveries suggest our frameworks of how stars drive the chemical transformation of galaxies remain incomplete, signifying we still do not fully comprehend the cosmic processes that produced the formation of planets like Earth and ultimately to our own existence. The narrative thickens further when we contemplate the configurations of these ancient galaxies. Webb has exposed that numerous distant galaxies possess flattened, oval, disc-like, and tube-like arrangements rather than the familiar spiral arms or elliptical shapes we observe in the local universe. This proved completely unanticipated and requires additional investigation to fully explain. It resembles discovering that ancient architecture followed completely different principles than modern construction techniques, generating structures that are both functional and aesthetically pleasing, yet operate according to rules we are only beginning to comprehend. These observations indicate that galaxy formation in the infant universe followed pathways that our current theories struggle to explain. Yet Webb has not merely found surprisingly vibrant early galaxies, it has also uncovered extremely dormant ones. These galactic corpses represent the remnants of intense star formation episodes at the cosmic dawn, galaxies that blazed bright and rapid before exhausting their fuel and falling into stellar dormancy. While these dormant galaxies had been detected previously by Hubble and ground-based observatories, Only Webb possessed the power to dissect their illumination with sufficient precision to expose how long they have been inactive. It resembles possessing a cosmic forensics laboratory that can determine not merely that something perished, but when and how it died, providing crucial clues about the life and termination cycles of galaxies in the primordial universe. The team behind Webb's early galaxy observations has been clear regarding the revolutionary nature of these discoveries. As one researcher explained, until James Webb, we never actually possessed observational data to help us comprehend the physics of the infant universe. The telescope is finally permitting us to bridge the gap between the theoretical Big Bang and the remarkable collection of cosmic objects we observe scattered across our night sky. These findings are forcing cosmologists to grapple with fundamental questions about the nature of dark matter, the efficiency of early star formation, and the basic timeline of cosmic development. Some researchers are beginning to wonder whether our frameworks can be stretched and modified to accommodate these unexpected findings, or whether we need to completely reconsider our comprehension of how the universe evolved from simplicity to complexity. The debate remains far from settled. Some scientists propose that star formation in the primordial universe was extraordinarily efficient, permitting massive galaxies to assemble considerably more quickly than in the modern cosmos. Others suggest that we may need to revise our comprehension of dark matter itself, the mysterious substance that provides the gravitational scaffolding around which galaxies develop. What proves certain is that Webb is providing us with observational information from an era of cosmic chronology that was previously accessible only through theoretical frameworks and computer simulations. For the first time, we are witnessing direct evidence of what the universe genuinely resembled when it was young, rather than relying on extrapolations and educated guesses based on what we observe in our local cosmic vicinity. The implications extend far beyond academic curiosity. These findings are rewriting our cosmic origin narrative, the story that explains how we progressed from a hot, dense, relatively simple early universe to the complex, structured cosmos we inhabit today. Comprehending these early epochs is not merely about satisfying human curiosity regarding our cosmic ancestry. It concerns comprehending the fundamental processes that govern how complexity emerges from simplicity, how structure develops from chaos, and how the raw materials of stars, planets, and life itself came to be distributed throughout the cosmos. As we stand on the threshold of these remarkable revelations, we are witnessing what may be the most significant paradigm transformation in cosmology since Edwin Hubble first discovered that the universe was expanding. Webb's observations of the primordial universe are demonstrating to us that cosmic development proceeded more rapidly, more efficiently, and more dramatically than we ever dared to imagine. Yet these findings in the distant universe represent merely the beginning of Webb's revolutionary impact on astronomy. The telescope's capabilities extend far beyond studying ancient galaxies, examining objects considerably closer to home, exposing secrets about planetary development, stellar transformation, and the potential for life itself to emerge in cosmic environments both familiar and utterly alien. The narrative of Webb's discoveries continues to be written, each observation adding new chapters to our comprehension of the cosmos. What we have explored this evening represents merely the opening pages of what promises to be an epic tale of cosmic discovery, one that will continue to unfold as this remarkable machine peers deeper into space and further back in time than any human-made instrument before it. As Webb directed its infrared observation from the distant cosmic dawn toward our own celestial vicinity, it began exposing secrets concealed in plain sight. The telescope's remarkable versatility permits it to study not merely the most ancient objects in the time's universe, but also worlds circling nearby stars, objects that might harbor the precise conditions necessary for life to flourish. Envision this for a moment. Merely 40 light-years from Earth, a small red dwarf star hosts 7 rocky planets compressed so tightly together that if you stood on one world, the others would appear larger in the sky than our moon appears from Earth. This is the TRAPPIST-1 system, discovered in 2017 and immediately recognized as one of the most intriguing planetary systems ever found. What renders TRAPPIST-1 so captivating is not merely the number of Earth-sized worlds it contains, but the tantalizing possibility that some of these planets might exist in that precious zone around their star where liquid water could survive on their surfaces. Red dwarf stars like TRAPPIST-1 are the most common type of star in our galaxy. If Earth-sized worlds orbiting red dwarfs can maintain atmospheres and potentially support liquid water, then the number of potentially habitable worlds in the Milky Way could be staggering. Yet there existed a problem. Red dwarf stars, while long-lived and stable, possess a violent youth. They tend to unleash powerful stellar flares and radiation that could strip away any atmospheres their planets might possess. For years, astronomers wondered whether the TRAPPIST-1 planets were barren, airless rocks scorched by their star's radiation, or whether some might have managed to retain the precious envelope of gas necessary to support liquid water and potentially life. Webb has begun to answer this question with unprecedented precision, and the results prove both illuminating and surprising. Utilizing its mid-infrared instrument, Webb made the first direct detection of thermal emission from a planet as small and cool as the rocky worlds in our own solar system. This represents a milestone that seemed almost impossible just a few years ago. The team focused their attention on TRAPPIST-1b, the innermost planet in the system. By measuring the heat energy radiating from this world in infrared wavelengths, they determined that its dayside temperature reaches approximately 500 Kelvin, roughly 450 degrees Fahrenheit. More importantly, these measurements suggest that TRAPPIST-1b lacks any significant atmosphere. It is a sobering reminder of how hostile space can be to the delicate conditions necessary for life as we know it. The intense radiation from the red dwarf star appears to have indeed stripped away any atmospheric gases that might have once surrounded this world, leaving behind a bare rock baking under the relentless energy of its nearby sun. Yet Webb's investigation did not stop there. The telescope turned its attention to TRAPPIST-1d, a world that sits farther out in the system where conditions might be more favorable for retaining an atmosphere. This planet occupies a position where liquid water could theoretically exist on its surface, making it a prime target for studying potentially habitable conditions beyond our solar system. The results published after careful analysis of Webb's spectroscopic data revealed that TRAPPIST-1d also lacks an Earth-like atmosphere. As Caroline Piale-Gorayeb from the University of Chicago explained, while we ultimately want to know if environments like Earth can exist elsewhere and under what conditions, Webb's observations allow us to rule out TRAPPIST-1d from our list of potential Earth twins or cousins. Yet even as some doors close, others open. Recent reanalysis of Webb's data on TRAPPIST-1b has revealed intriguing new possibilities. Different observational techniques and wavelengths can reveal varying aspects of these alien worlds, and fresh analysis suggests that the innermost planet might actually possess a hazy carbon dioxide-rich atmosphere after all. Alternatively, the measurements might indicate something equally fascinating, an unexpectedly high surface temperature that could suggest the world is geologically active, perhaps roiling with volcanic activity that continuously replenishes atmospheric gases, even as stellar radiation tries to strip them away. This highlights one of the most remarkable aspects of Webb's capabilities. The telescope can study these distant worlds using multiple techniques, each revealing different pieces of the puzzle. It resembles having several different microscopes, each designed to see aspects of a specimen that others cannot detect. The implications of these studies extend far beyond the TRAPPIST-1 system itself. By understanding how atmospheres survive or fail to survive around red dwarf stars, we are learning fundamental lessons about planetary habitability throughout the galaxy. These observations help astronomers refine their models of which types of worlds might be capable of supporting life and under what conditions. Yet Webb's exploration of alien worlds has not been limited to potentially habitable planets. The telescope has also turned its attention to the most massive objects in the JWST universe, supermassive black holes that lurk at the centers of galaxies and shape the cosmic landscape through their immense gravitational influence. What Webb discovered about these cosmic monsters has been nothing short of revolutionary. In the constellation Telescopium, the telescope detected a small red compact object that existed merely 500 million years after the Big Bang. This unassuming little red dot harbors what may be the earliest known black hole in the universe, a gravitational giant that challenges everything we thought we knew about how these objects form and grow. The black hole at the center of galaxy CEER SLRD Z9 weighs in at approximately 38 million times the mass of our Sun, making it roughly 10 times more massive than Sagittarius A star, the supermassive black hole that anchors our own Milky Way galaxy. Yet here is what makes this discovery truly mind-bending. This ancient black hole contains approximately 5% of the total mass of all the stars in its host galaxy, a ratio that far exceeds anything we observe in the modern universe. Stephen Finkelstein, one of the astronomers involved in this discovery, captured the significance perfectly when he noted that this adds to growing evidence that early black holes grew much faster than we thought possible, or they started out far more massive than our models predict. The implications are staggering. In the modern universe, supermassive black holes typically contain only about 0.1% of their host galaxy's stellar mass. Finding a black hole with such a disproportionate mass so early in cosmic history suggests that these objects were not just larger than expected, but were growing at rates that seem to defy our understanding of how matter can be consumed by gravitational fields. The mystery deepened when Webb detected the most distant black hole merger ever observed. In May 2024, the telescope identified evidence of two massive black holes in the process of combining within the galaxy system ZS7, an event occurring just 740 million years after the Big Bang. This represents not just a record for distance, but the first time such a phenomenon has been detected so early in cosmic history. Black hole mergers are among the most energetic events in the universe, releasing more energy in gravitational waves than all the stars in the observable universe emit in light. The fact that such mergers were already occurring within the first billion years after the Big Bang suggests that supermassive black holes achieved their enormous masses through rapid growth and frequent collisions, even in the universe's youth. Perhaps most intriguingly, Webb has potentially identified evidence for direct collapse black holes, massive objects that form not through the gradual growth of stellar remnants, but through the catastrophic collapse of enormous gas clouds. In the Cosmos Web Survey, astronomers discovered an unusual object nicknamed the Infinity Galaxy, displaying the distinctive shape of two compact red nuclei surrounded by rings, resembling the mathematical infinity symbol. This bizarre structure appears to have formed through the head-on collision of two disk galaxies. Yet what makes it truly remarkable is the supermassive black hole position between the two nuclei, sitting within a vast expanse of gas. The team proposes that this black hole formed through direct collapse of the gas cloud itself, a process that may explain how some of the incredibly massive black holes Webb has found in the early universe could have achieved their enormous sizes so quickly. These direct collapse scenarios represent a kind of cosmic shortcut, allowing black holes to skip the usual slow process of growth from stellar mass objects and instead begin their existence already weighing millions of times more than our Sunday. It resembles finding evidence that some mountains formed not through gradual geological processes, but by having enormous chunks of rock dropped from space fully formed. Yet perhaps the most extreme discovery came from Webb's observation of a black hole feeding at rates that should not be possible, according to our understanding of physics. Using data from both Webb and the Chandra X-ray Observatory, astronomers identified a low-mass supermassive black hole just 1.5 billion years after the Big Bang that is consuming matter at more than 40 times the theoretical limit. This phenomenon, known as super-Eddington accretion, occurs when a black hole consumes matter faster than radiation pressure should theoretically allow. It resembles discovering a drain that somehow manages to empty a bathtub faster than water can flow into it, defying our understanding of the physical processes involved. Hee-Won Soo from the International Gemini Observatory, who led the research team, explained that this discovery suggests a significant portion of mass growth can occur during a single episode of rapid feeding, regardless of whether the black hole originated from a light or heavy seed. These feeding frenzies, while short-lived, could help explain how supermassive black holes grew to their enormous sizes within the relatively brief time frame of the early universe. The black hole discoveries represent more than just individual objects of interest. They are revealing fundamental truths about how the universe organized itself in its earliest epochs. The relationship between supermassive black holes and their host galaxies appears to have been established very early in cosmic history, suggesting that these gravitational giants played a crucial role in shaping the structure and evolution of the cosmos itself. As Webb continues to peer deeper into space and further back in time, each discovery adds new pieces to the puzzle of cosmic evolution. The telescope is showing us that the early universe was not the simple, quiet place we once imagined, but a dynamic, rapidly evolving cosmos where massive structures formed with surprising speed and efficiency. These revelations about black holes and distant galaxies represent just a fraction of Webb's transformative impact on astronomy. The telescope's versatility allows it to study phenomena across an enormous range, too, of scales. From the smallest brown dwarf stars to the largest structures in the cosmos, each observation contributing to our growing understanding of how the universe works. The story takes another remarkable turn when we venture beyond the familiar boundaries of our own galaxy. For decades, astronomers have catalogued thousands of brown dwarfs, those enigmatic objects that exist in the twilight between planets and stars, too massive to be planets, yet lacking the nuclear fires that define true stars. These cosmic misfits have been found scattered throughout the Milky Way, but always within our galactic neighborhood. Then Webb achieved something that seemed almost impossible. It detected the first rich population of brown dwarf candidates beyond our galaxy, nestled within the star cluster NGC 602. Elena Manjavakis, from the Space Telescope Science Institute, captured the significance of this discovery perfectly when she noted that until now, we had known of approximately 3,000 brown dwarfs, but they all lived inside our own galaxy. This represents more than just extending our catalogue of celestial objects. By studying these young, metal-poor brown dwarfs in an environment completely different from our local galactic neighborhood, astronomers are gaining insights into how stars and planets formed under the harsh conditions that prevailed in the early universe. It resembles discovering artifacts from an ancient civilization in a previously unexplored continent, artifacts that reveal how people lived and worked under conditions completely unlike anything in the modern world. Yet Webb did not stop at finding brown dwarfs in distant galaxies. It pushed the boundaries of what we thought possible in star formation itself. The telescope identified the new record holder for the smallest free-floating brown dwarf ever discovered, an object with only 3 to 4 times the mass of Jupiter, drifting alone through space without a parent star. Kevin Luhman from Pennsylvania State University, who led this research, explained that one of the most basic questions in astronomy textbooks is simply, what are the smallest stars? Webb is helping us answer that fundamental question by identifying objects that challenge our understanding of the minimum mass required for stellar formation. This tiny brown dwarf, along with 2 other ultra-low mass objects discovered in the same survey, represents the extreme lower limit of what can form through star-like processes. These objects are so small and cool that they blur the line between failed stars and massive planets, forcing astronomers to reconsider the fundamental mechanisms that govern how matter collapses under gravity to form distinct types of cosmic objects. The discovery becomes even more intriguing when we consider that Webb has also found brown dwarfs surrounded by protoplanetary disks, the swirling disks of dust and gas from which planets are born. In the Orion Nebula, the Telescope confirmed 20 brown dwarfs with these planet-forming disks, demonstrating that even these failed stars can retain the raw materials necessary for planetary formation. This revelation challenges previous models that suggested brown dwarfs would be too small and cool to maintain the conditions necessary for planet formation. Instead, Webb is showing us that the processes that lead to planetary systems might be far more widespread and diverse than we ever imagined. It resembles discovering that not only can small businesses succeed in challenging economic environments, but they can also spawn entire ecosystems of related enterprises. The implications ripple through our understanding of how common planetary systems might be throughout the galaxy. If even brown dwarfs can form planets, then the number of worlds in our cosmic neighborhood could be far larger than our most optimistic estimates. Webb's versatility extends even closer to home, studying objects within our own solar system with unprecedented detail. When astronomers discovered asteroid 2024 YR4 in December 2024, they faced a critical challenge. This space rock has a very small but non-zero chance of impacting Earth in 2032, yet determining the actual hazard it poses requires knowing its precise size. The problem is that visible light observations can only tell us how bright the asteroid appears, not how large it actually is. A small, highly reflective asteroid can appear just as bright as a large, dark one. Current estimates place 2024 YR4 somewhere between 40 and 90 meters across, a range that makes all the difference when assessing potential impact hazards. Webb's infrared capabilities offer a solution. Instead of relying on reflected visible light, the telescope can measure the heat that the asteroid emits directly. This thermal emission provides a much more accurate assessment of the object's actual size, helping scientists determine whether we are dealing with a 40-meter rock that would likely burn up in Earth's atmosphere or a 90-meter boulder that could cause significant damage if it reached the surface. This demonstrates how Webb's revolutionary technology serves not just our cosmic curiosity, but also our practical needs as inhabitants of a planet that orbits through a solar system filled with potentially hazardous objects. The telescope represents our most advanced early warning system for threats that could emerge from the depths of space. Yet Webb's solar system observations extend far beyond potentially dangerous asteroids. The telescope has studied interstellar visitors like Comet 3I, Atlas, objects that originate outside our solar system and provide unique insights into the composition and conditions of other stellar neighborhoods. These interstellar wanderers offer a rare opportunity to sample material that formed around distant stars, carrying with them chemical signatures that reveal the processes at work in alien solar systems. Because these objects are just passing through, astronomers must use every available tool to study them before they disappear back into the cosmic darkness forever. Webb's observations of interstellar comets represent a form of cosmic archaeology, allowing us to analyze samples from distant regions of the galaxy without the need for interstellar travel. It resembles having visitors from foreign countries arrive at your doorstep, carrying artifacts that reveal the culture and conditions of their homeland. The telescope has also turned its attention to some of the most beautiful and complex structures in our local cosmic neighborhood. When Webb observed the intricate patterns of interstellar dust and gas, it revealed details resembling the knots and whorls of wood grain, structures so fine and complex that they left astronomers genuinely shocked. Jacob Janssen, from Caltech, principal investigator of one such study, captured the team's amazement when he noted that they were pretty shocked to see this level of detail. The observations revealed layers like an onion, structures that astronomers believe exist throughout the galaxy but had never been able to see inside before. These observations are allowing scientists to map the true three-dimensional structure of the interstellar medium for the first time, revealing how matter flows and organizes itself in the spaces between stars. It resembles having a detailed topographical map of an ocean floor that was previously hidden beneath murky waters. Closer to home, Webb has provided extraordinary new views of familiar objects in our own solar system. The telescope's observations of Jupiter revealed previously unseen features above the planet's iconic Great Red Spot, a region that was previously thought to be relatively unremarkable, but actually hosts a variety of intricate structures and activity. Webb's infrared vision has captured new details of auroras dancing in Jupiter's atmosphere, phenomena that result from the interaction between the planet's powerful magnetic field and charged particles streaming from the sunday. These observations demonstrate how Webb can study planetary atmospheres within our own solar system with unprecedented detail and precision. The telescope has also provided crucial insights into Saturn's moon Titan, that enigmatic world shrouded in a thick, hazy atmosphere of nitrogen and methane. By combining Webb's data with observations from ground-based telescopes, scientists have observed evidence of cloud convection in Titan's northern hemisphere for the first time. Most of Titan's lakes and seas are located in this northern region, and they are likely replenished by occasional rains of methane and ethane. Webb has detected key carbon-containing molecules that provide insight into the chemical processes operating in Titan's complex atmosphere, revealing details about the methane cycle that operates on this distant moon, much like the water cycle on Earth. But at temperatures hundreds of degrees colder, these observations of Titan represent more than just planetary science. They provide insights into the kinds of chemical processes that might operate on worlds throughout the galaxy, worlds where conditions are too extreme for liquid water, but where other substances might create the complex chemistry necessary for life as we do not yet know it. Throughout all of these discoveries, from the most distant galaxies to objects in our own solar system, Webb is demonstrating something profound about the nature of scientific exploration itself. Each observation builds upon previous knowledge while simultaneously opening new questions that we had not even known to ask. The telescope is revealing that the universe operates on principles of complexity and interconnection that extend across all scales of space and time. The same physical laws that govern the formation of the earliest galaxies also determine how dust organizes itself in nearby nebulae. The same processes that create heavy elements in stellar cores also influence the composition of asteroids in our own solar system. Webb is showing us that astronomy is not just about cataloging distant objects, but about understanding the fundamental processes that connect everything from the smallest particles to the largest structures in the cosmos. Each discovery adds another thread to the vast tapestry of cosmic understanding, revealing patterns and relationships that speak to the underlying unity of physical law throughout the universe. As we continue this journey through Webb's discoveries, we find ourselves confronting not just new facts about the cosmos, but new ways of thinking about our place within it. The telescope is revealing a universe that is simultaneously more strange and more comprehensible than we ever imagined. A cosmos where the familiar and the alien coexist in patterns of breathtaking beauty and complexity. The story of Webb's discoveries is far from over. Each day brings new observations, new data, new insights that challenge our assumptions and expand our understanding. What we have explored represents just the beginning of what promises to be a revolution in cosmic knowledge, one that will continue to unfold as this remarkable machine peers deeper into the mysteries of space and time than any human instrument before it. As Webb's revolutionary gaze swept across the cosmos, it began to unveil secrets that exist in the shadowy realm between the familiar and the utterly alien. In distant star-forming regions, where cosmic nurseries birth new suns from clouds of gas and dust, the sun's telescope discovered phenomena that challenge our most basic assumptions about how stellar systems come to be. Picture vast stellar nurseries where baby stars are taking their first breaths, surrounded by swirling disks of material that will eventually coalesce into planets, moons, and the toning, building blocks of complexity itself. Webb has peered into these cosmic cradles with unprecedented clarity, revealing structures so intricate and beautiful that they seem almost too perfect to be real. In one particularly striking observation, the telescope examined a stellar nursery where jets of superheated gas shoot outward from newly formed stars at velocities that stagger the imagination. These stellar jets, invisible to our eyes but blazing bright in Webb's infrared vision, carve through surrounding clouds like cosmic lightsabers, sculpting the very environment from which future planetary systems will emerge. What makes these observations truly remarkable is not just their beauty, but what they reveal about the violent yet creative processes that govern star formation. Each jet represents a young star learning to regulate its own growth, ejecting excess material that would otherwise cause it to collapse under its own weight. It is a delicate cosmic balancing act, one that determines whether a star will live a long, stable life, capable of nurturing planetary companions, or burn out quickly in a brief but spectacular display. Yet Webb's most haunting discoveries come from regions where stars have already lived out their entire cosmic stories. When massive stars exhaust their nuclear fuel, they do not simply fade away quietly. Instead, they explode in cataclysmic events called supernovae, scattering the heavy elements forged in their cores across vast regions of space. Webb has observed the aftermath of these stellar deaths with exquisite detail, revealing expanding shells of glowing gas enriched with the very elements that make planets and life possible. Carbon, oxygen, silicon, iron, all the materials that form the foundation of terrestrial worlds and biological complexity are distributed through these spectacular stellar obituaries. In one particularly moving observation, Webb captured the remnant of a supernova that exploded centuries ago, its expanding shell of debris still glowing with the heat of its violent birth. Within this cosmic graveyard, new stars are already beginning to form, fed by the enriched material scattered by their stellar ancestor. It is a profound reminder of the cyclical nature of cosmic evolution, where death and birth are intimately connected in an endless dance of renewal. The telescope has also revealed something unexpected about how these stellar explosions shape their surrounding environments. Rather than simply blasting material outward in all directions, supernovae create complex three-dimensional structures that channel and direct the flow of enriched gas. These structures act like cosmic highways, guiding heavy elements toward regions where they can be incorporated into the next generation of stars and planets. This discovery has profound implications for understanding how planets like Earth acquired the diverse chemical elements necessary for geological complexity and biological evolution. The distribution of heavy elements throughout the galaxy is not random, but follows patterns established by the intricate geometry of ancient stellar explosions. Webb's observations extend beyond individual stars to encompass entire stellar populations in globular clusters, ancient collections of stars that formed when the universe was young. The telescope has revealed details about stellar evolution that were previously hidden. These stellar cities contain some of the oldest stars in the galaxy, cosmic time capsules that preserve information about conditions in the cosmic time. Early universe. By studying the light from these ancient stars, astronomers can reconstruct the chemical history of our galaxy, tracing how successive generations of stellar death and birth have gradually enriched the cosmic environment with the elements necessary for planetary formation and biological complexity. Yet perhaps Webb's most philosophically significant discoveries involve the detection of organic molecules in space. In the cold, dark regions between stars, where temperatures hover just above absolute zero, the telescope has identified complex carbon-based compounds that serve as the building blocks of biological chemistry. These molecules, floating in the vast emptiness between stellar systems, suggest that the chemical precursors of life are not rare cosmic accidents, but common features of the galactic environment. Ice-coated dust grains in interstellar space serve as cosmic chemistry laboratories where simple molecules combine over millions of years to create increasingly complex organic compounds. When new stars form and their radiation heats these frigid regions, these organic molecules are released into the surrounding space where they can be incorporated into forming planetary systems. This means that planets may begin their existence already seeded with the chemical ingredients necessary for biological evolution. Webb has traced these organic molecules from their formation in interstellar space to their incorporation into the atmospheres of distant exoplanets. The telescope can detect the spectroscopic signatures of these compounds in the atmospheres of alien worlds, providing our first direct evidence of complex chemistry operating on planets orbiting other stars. In one particularly intriguing observation, Webb detected water vapor, carbon dioxide, and complex organic molecules in the atmosphere of an exoplanet orbiting a star similar to our own Sunday. While this world is too hot to support life as we know it, the detection of these compounds demonstrates that the chemical ingredients for biology can survive the violent processes of planetary formation and remain available for potential biological evolution. These atmospheric studies represent a new frontier in the search for life beyond Earth. By analyzing the chemical composition of exoplanet atmospheres, astronomers can begin to identify worlds where the conditions might be suitable for biological processes to take hold and flourish. Yet, Webb's atmospheric studies have also revealed how fragile these conditions can be. The telescope has observed exoplanets where stellar radiation has stripped away most of their atmospheric gases, leaving behind barren worlds that might once have possessed the ingredients for habitability. These observations serve as sobering reminders of how delicate the balance must be for worlds to maintain the conditions necessary for life over geological timescales. The telescope has also made groundbreaking observations of rogue planets, worlds that have been ejected from their original stellar systems and now wander alone through the cosmic darkness. These orphaned worlds, invisible to conventional telescopes because they emit no light of their own, glow faintly in the infrared radiation that Webb can detect. The discovery of these wandering worlds suggests that planetary formation is an even more chaotic process than previously imagined. Gravitational interactions during the early stages of stellar system formation can fling planets into interstellar space, where they spend eternity drifting through the void between stars. Some of these rogue planets might retain enough internal heat to maintain subsurface oceans beneath frozen surfaces, creating potential habitats for life that exist completely independent of any star. These dark worlds challenge our star-centric view of habitability and suggest that life might find ways to survive in environments we had never considered. Webb's observations of stellar nurseries have also revealed the incredible diversity of planetary system architectures. Rather than the orderly arrangement we see in our own solar system, with small rocky planets close to the Sun and large gas giants farther out, many stellar systems display configurations that seem almost random. The telescope has observed systems where massive planets orbit extremely close to their parent stars, completing full orbits in just a few days. Other systems contain multiple planets locked in complex gravitational resonances, their orbits synchronized like the movements of a cosmic clockwork mechanism. These diverse architectures suggest that planetary formation is influenced by countless variables, from the initial composition of the stellar nursery to the timing of various formation processes to random gravitational encounters that can reshape entire systems. Each planetary system tells its own unique story of cosmic evolution. In studying these varied planetary arrangements, Webb is helping astronomers understand why our own solar system has the particular configuration it does. The orderly spacing of our planets, with terrestrial worlds in the inner system and gas giants in the outer regions, appears to be just one possible outcome among many different evolutionary pathways. The telescope has also made remarkable discoveries about the moons of gas giant planets in our own solar system. Webb's observations of Jupiter's moons have revealed active geological processes that were previously undetected. Volcanic activity on Io, the most volcanically active body in the solar system, appears to be even more dynamic than previously realized. On Europa, Jupiter's ice-covered moon, Webb has detected plumes of water vapor erupting from the surface, providing direct evidence of the subsurface ocean that lies beneath the frozen shell. These plumes offer a potential pathway for studying the chemistry of Europa's hidden sea without the need to drill through kilometers of ice. Similar observations of Saturn's moon Enceladus have revealed that its subsurface ocean contains complex organic molecules, suggesting that this distant world possesses the chemical ingredients necessary for biological processes. The detection of these compounds in the plumes that Enceladus ejects into space provides tantalizing hints that life might exist in environments completely unlike anything on Earth. These discoveries about icy moons throughout our solar system have profound implications for the search for life beyond Earth. Rather than focusing solely on planets that orbit within the habitable zones of their stars, astronomers are beginning to realize that moons with subsurface oceans might be among the most promising places to search for biological activity. Webb's studies of these icy worlds are revealing that liquid water, one of the key requirements for life as we know it, might be far more common throughout the galaxy than previously imagined. Tidal heating from massive parent planets can maintain liquid oceans beneath ice shells for billions of years, creating stable environments where biological evolution could potentially occur. The telescope has also made unexpected discoveries about the composition of comets, those ancient wanderers that preserve samples of the original materials from which our solar system formed. Webb's spectroscopic analysis of comet atmospheres has revealed complex organic molecules that formed in the frigid outer regions of the early solar system. These comets serve as cosmic time capsules, carrying pristine samples of the materials that existed during the earliest phases of planetary formation. By studying their composition, astronomers can reconstruct the chemical environment in which Earth and the other terrestrial planets formed billions of years ago. The organic compounds detected in comets include some of the same molecules that are essential for biological processes on Earth. This supports the hypothesis that comets may have delivered some of the chemical ingredients necessary for life during the late, heavy bombardment period, when these ancient objects frequently collided with the inner planets. Webb's observations are revealing that the boundary between astronomy and biology is far more fluid than we once imagined. The telescope is showing us that the chemical processes that lead to biological complexity operate throughout the cosmos, from the cold depths of interstellar space to the warm surfaces of potentially habitable exoplanets. As we trace these connections between stellar evolution, planetary formation, and the emergence of biological complexity, we begin to see our own existence not as an isolated cosmic accident, but as part of a vast network of physical and chemical processes that operate throughout the universe. Each observation adds another piece to this cosmic puzzle, revealing new connections and relationships that help us understand our place in the grand scheme of cosmic evolution. Webb is showing us that we are not separate from the universe we study, but intimately connected to its deepest processes and most fundamental patterns. The telescope continues to push the boundaries of what we thought possible in astronomical observation, revealing phenomena that challenge our theories and expand our imagination. Each new discovery opens doors to questions we had not even known to ask, ensuring that the journey of cosmic discovery will continue for generations to come. As Webb peers deeper into space and further back in time, it carries with it our hopes and dreams, our curiosity and wonder, our deep human need to understand our place in the vast cosmic story. The discoveries we have explored this evening represent just the beginning of what promises to be the most remarkable period of astronomical discovery in human history. The revelations continue to cascade from Webb's observations, each more extraordinary than the last. As the telescope turned its attention to some of the most enigmatic objects in the cosmos, it began to uncover secrets about cosmic phenomena that exist at the very edges of our understanding. In the heart of active galaxies, where supermassive black holes devour matter with an appetite that defies comprehension, Webb has observed jets of material streaming outward at velocities approaching the speed of light. These cosmic fountains, stretching across distances that dwarf entire star systems, represent some of the most powerful forces in the universe. What makes these observations truly remarkable is not just the scale of these phenomena, but the precision with which Webb can study them. The telescope can trace individual knots of material as they race along these jets, revealing how energy and matter behave under conditions so extreme that they exist nowhere else in the natural world. These jets serve as cosmic laboratories where the fundamental laws of physics are pushed to their absolute limits. The material within them experiences gravitational fields billions of times stronger than anything we encounter on Earth, temperatures that exceed those found in stellar cores, and magnetic fields so intense they could influence matter from distances measured in light years. By studying these extreme environments, astronomers are testing our understanding of relativity, quantum mechanics, and plasma physics in regimes that no Earth-bound laboratory could ever hope to replicate. Each observation provides new insights into how matter and energy behave when subjected to forces that stretch the very fabric of space-time itself. Yet Webb's most haunting discoveries come from regions where galaxies themselves are dying. In cosmic graveyards scattered throughout the universe, the telescope has observed the final moments of galactic evolution, where stellar formation has ceased and entire stellar populations are fading into darkness. These galactic fossils tell stories of cosmic violence and renewal that span billions of years. Some died quietly, exhausting their reserves of star-forming gas over countless eons until no new suns could ignite. Others met more violent ends, torn apart by gravitational encounters with neighboring galaxies or consumed by the ravenous appetite of central black holes. In one particularly poignant observation, Webb captured a galaxy in the process of being slowly dismembered by its larger neighbor. Streams of stars, gas, and dust stretch between the two systems like cosmic bridges, carrying the smaller galaxy's substance into the gravitational embrace of its massive companion. This celestial cannibalism represents one of the fundamental processes that have shaped cosmic evolution since the earliest epochs. Larger galaxies grow by consuming their smaller neighbors, a process that continues today throughout the universe. Webb's observations allow us to witness this cosmic recycling in exquisite detail, seeing how matter flows from one cosmic structure to another across scales that boggle the imagination. The telescope has also revealed the unexpected beauty hidden within cosmic destruction. When galaxies collide and merge, the gravitational chaos triggers spectacular bursts of star formation. Webb has observed these stellar baby booms in unprecedented detail, seeing how the violent mixing of galactic materials creates conditions perfect for nurturing new generations of suns. In these collision zones, stars form at rates hundreds of times faster than in quiescent galaxies like our own Milky Way. The night sky of a planet in such a system would blaze with the light of countless newborn stars, creating celestial displays of unimaginable beauty and intensity. These starburst galaxies burn bright but briefly in cosmic terms. Their furious pace of stellar formation exhausts available raw materials within just a few million years, leaving behind populations of massive stars that will themselves explode as supernovae in relatively short order. It is cosmic evolution accelerated to breakneck speeds. Webb's infrared vision allows it to peer through the dust clouds that shroud these stellar nurseries, revealing the intricate structures within. The telescope has observed spiral patterns, shock waves, and turbulent flows that sculpt the distribution of star-forming material with artistic precision. These observations reveal that even in the most chaotic cosmic environments, physical processes create patterns of startling regularity and beauty. Gravity, magnetism, and fluid dynamics work together to organize matter into structures that follow mathematical relationships as elegant as any human artwork. The telescope has also made groundbreaking discoveries about the role of magnetic fields in cosmic evolution. These invisible forces, which extend across vast regions of space, help channel the flow of matter and energy throughout the universe. Webb can detect the subtle effects of these fields by observing how they influence the polarization of light from distant objects. In star-forming regions, magnetic fields act like cosmic shepherds, guiding the collapse of gas clouds and determining where and how new stars will be born. In the spaces between galaxies, these same fields help organize the flow of matter along the cosmic web, the vast network of dark matter filaments that connects all large-scale structures in the universe. The discovery that magnetic fields play such a crucial role in cosmic organization has profound implications for our understanding of how the universe evolved from the relatively smooth conditions that existed shortly after the Big Bang to the complex, structured cosmos we observe today. Webb has also revealed unexpected connections between the largest and smallest scales in the universe. The telescope's observations show that the same physical processes that govern the behavior of individual atoms also determine how entire galaxy clusters evolve over billions of years. Quantum mechanical effects that operate on subatomic scales influence the behavior of matter in the extremely low-density environments found between galaxies. Meanwhile, gravitational processes that shape the largest cosmic structures also determine how matter flows within individual stellar systems. These connections suggest that the universe operates as a unified system where phenomena occurring on vastly different scales are intimately linked through the fundamental laws of physics. Webb is revealing a cosmos that is simultaneously more complex and more comprehensible than we ever imagined. The telescope has made particularly intriguing discoveries about dark matter, that mysterious substance that outweighs ordinary matter by a factor of 5 throughout the universe. While dark matter does not emit or absorb light, Webb can detect its presence through its gravitational effects on visible matter. In galaxy clusters, the most massive structures in the universe, Webb has observed how dark matter sculpts the distribution of ordinary matter into intricate patterns. These observations provide crucial tests of our theories about dark matter's properties and behavior. The telescope has detected subtle distortions in the shapes of distant galaxies caused by the gravitational lensing effects of intervening dark matter concentrations. These cosmic mirages allow astronomers to map the distribution of dark matter throughout the universe with unprecedented precision. These dark matter maps reveal a cosmos dominated by vast networks of invisible scaffolding, within which ordinary matter organizes itself into the stars and galaxies we can observe. It resembles discovering that a familiar landscape is actually supported by an elaborate but invisible architecture that determines every visible feature. Webb's observations are also shedding light on the nature of dark energy, the mysterious force that drives the accelerating expansion of the universe. By studying how cosmic structures have evolved over billions of years, the telescope provides crucial data for understanding this enigmatic component of the cosmos. The expansion of space itself affects how light travels from distant objects to our telescopes. Webb can measure these effects with extraordinary precision, providing new insights into how dark energy has influenced cosmic evolution throughout the universe's history. These measurements suggest that dark energy's influence has not been constant throughout cosmic time. Instead, its effects appear to have changed as the universe has aged, with implications that could revolutionize our understanding of the cosmos's ultimate fate. As Webb continues its observations, it is becoming clear that we are witnessing not just individual discoveries, but a fundamental shift in how we understand the universe itself. The telescope is revealing a cosmos that operates according to principles of connection and relationship that extend across all scales of space and time. Each observation builds upon previous knowledge while simultaneously opening new avenues of investigation. The telescope is showing us that the universe is not a collection of isolated objects, but a unified system where everything influences everything else through networks of physical relationship that span the entire observable cosmos. The discoveries we have explored represent more than scientific achievements. They are revelations about the nature of existence itself, about how complexity emerges from simplicity, how order arises from chaos, and how the fundamental forces of nature conspire to create a universe capable of contemplating its own existence. Webb is teaching us that we are not merely observers of cosmic phenomena, but participants in the very processes we study. The atoms in our bodies were forged in stellar cores. The energy that powers our thoughts flows from nuclear reactions in our sunday, and the gravitational fields that keep us anchored to Earth extend throughout the cosmos, connecting us to the most distant galaxies. As the telescope continues its revolutionary survey of the cosmos, each new observation adds another thread to the vast tapestry of cosmic understanding. We are witnessing the birth of a new astronomy, one that reveals connections and relationships between phenomena that were previously thought to be completely separate. The story of Webb's discoveries is far from complete. The telescope has only just begun to explore the cosmic landscape, and each day brings new observations that challenge our assumptions and expand our understanding. What we have explored this evening represents just a fraction of the revolutionary insights that this remarkable machine will provide over its operational lifetime. The journey continues, carrying us deeper into the mysteries of space and time, revealing truths about the universe that will transform how we see ourselves and our place in the grand cosmic story. Webb is not just showing us what the universe looks like, it is showing us what the universe means and how every aspect of cosmic evolution has contributed to the remarkable emergence of consciousness, capable of contemplating its own origins. In the quiet darkness of space, 1 million miles from Earth, this extraordinary machine continues its patient work, gathering photons that have traveled across billions of years of cosmic history. Each particle of light carries with it information about phenomena so distant in space and time that they existed before our sun was born, before our galaxy took its current shape, before the conditions necessary for life had even begun to emerge. Yet somehow, through the remarkable convergence of human ingenuity and cosmic circumstance, we find ourselves capable of capturing and interpreting these ancient messengers. Webb represents the culmination of countless human dreams and aspirations, a testament to our species' irrepressible desire to understand the universe that gave birth to us. The telescope continues its observations, each one adding new chapters to the greatest story ever told, the story of how the universe evolved from simplicity to complexity, from darkness to light, from silence to the process, emergence of minds capable of wonder. And in that ongoing story, we find not just scientific knowledge, but something deeper and more profound, an understanding of our place in the vast interconnected web of cosmic existence. The revelations streaming from Webb's instruments have begun to paint a picture of cosmic evolution that is simultaneously more violent and more beautiful than we ever dared imagine. As the telescope peers into the most distant reaches of space and time, it is uncovering evidence of processes that operated when the universe was barely recognizable compared to the cosmos we inhabit today. In those primordial epochs, when the universe was still finding its rhythm after the chaos of creation, Webb has detected something that challenges our most fundamental assumptions about how cosmic structures form and evolve. The telescope has observed what appears to be fully mature stellar systems existing at times when our models suggest they should still be in their infancy. These ancient stellar populations display chemical signatures that seem almost impossible given the brief time available for their formation. The heavy elements detected in their spectra should have required multiple generations of stellar death and rebirth to accumulate. Yet here they are, shining in the cosmic dawn when the universe was still learning how to make stars at all. It resembles discovering a master craftsman's workshop in a newly founded settlement, complete with tools and techniques that should have taken centuries to develop. The implications ripple through our understanding of stellar evolution, forcing astronomers to reconsider whether the early universe operated according to rules we have not yet learned to recognize. Yet perhaps even more intriguing are Webb's observations of cosmic voids, those vast empty regions that exist between the great filaments of the cosmic web. For decades, these spaces were thought to be nearly empty cosmic deserts where little of interest occurs. Webb has revealed that these supposedly barren regions harbor their own subtle but profound mysteries. Within these cosmic expanses, the telescope has detected faint streams of matter flowing along invisible gravitational currents, like rivers running through a landscape we cannot see. These flows suggest that even the most apparently vacant regions of space are actually threaded with complex networks of dark matter filaments, creating pathways along which ordinary matter can travel across cosmic distances. The discovery transforms our understanding of how matter moves throughout the universe. Rather than simply falling toward massive structures under gravitational attraction, material appears to follow elaborate highway systems that span hundreds of millions of light years. These cosmic transit routes help explain how galaxies can maintain steady supplies of fresh material for star formation over billions of years. Webb has also made disturbing discoveries about the fate of matter that falls into these cosmic transportation networks. The telescope has observed streams of gas that appear to be heating up as they flow along these invisible channels, glowing with thermal radiation that suggests they are being compressed and accelerated by forces we are only beginning to understand. This heating process has profound implications for galactic evolution. As fresh material flows towards star-forming regions, it may become too hot to easily condense into new stars, potentially limiting the rate at which galaxies can grow and evolve. The cosmic web is not just a passive framework for organizing matter. It is an active participant in determining how efficiently the universe can create complexity. The telescope's observations extend beyond individual cosmic structures to encompass the universe's overall architecture. Webb has begun to map the three-dimensional distribution of matter throughout space with unprecedented precision, revealing patterns that extend across the entire observable cosmos. These cosmic surveys show that the universe's large-scale structure resembles a vast biological organism, with dense nodes connected by filamentary networks that pulse with flows of matter and energy. The resemblance to neural networks or circulatory systems is so striking that some astronomers have begun to wonder whether the universe itself might possess forms of organization that we are only beginning to recognize. The implications are both humbling and inspiring. If the cosmos operates according to principles of organization that mirror biological systems, it suggests that the emergence of life and intelligence might not be cosmic accidents, but natural consequences of the browing universe's tendency to create increasingly complex forms of order. Webb has also made groundbreaking discoveries about how information flows throughout the cosmic web. The telescope can detect subtle correlations in the properties of galaxies separated by vast distances, correlations that suggest these systems are somehow connected through processes that operate faster than light can travel between them. These quantum-like correlations on cosmic scales challenge our understanding of causality and locality. If widely separated regions of the universe can maintain coordinated behavior, it implies the existence of communication mechanisms that transcend the speed of light limitation that governs most physical processes. The phenomenon may be related to quantum entanglement, where particles that have interacted in the past maintain mysterious connections regardless of the distance that separates them. If similar processes operate on cosmic scales, it would mean that the universe possesses forms of unity that extend far beyond anything we have previously imagined. As Webb continues to probe these cosmic mysteries, each observation raises new questions about the nature of reality itself. The telescope is revealing a universe that operates according to principles of connection and relationship that we are only beginning to comprehend. The discoveries extend to our understanding of time itself. Webb's observations of the most distant objects reveal that cosmic evolution has not proceeded at the steady, predictable pace that our theories suggest. Instead, the early universe appears to have experienced periods of accelerated development, punctuated by intervals of relative stability. These temporal irregularities suggest that cosmic history we've been shaped by events and processes that operated on timescales we have not properly accounted for in our models. The universe may have experienced growth spurts and quiet periods, much like a living organism, rather than evolving at the constant rate assumed by most cosmological theories. The telescope has detected evidence of ancient cosmic catastrophes that temporarily disrupted the normal course of galactic evolution. These events, possibly related to the merger of supermassive black holes or the collision of dark matter structures, appear to have triggered periods of intense activity, followed by long intervals of recovery. Understanding these temporal patterns has profound implications for predicting the universe's future evolution. If cosmic development proceeds in fits and starts rather than at a steady pace, it means that our current epoch may be either a period of relative calm before another burst of activity, or the beginning of a long decline toward cosmic senescence. Webb's most philosophically challenging discoveries involve observations that seem to suggest the universe possesses forms of memory. The telescope has detected correlations between the properties of cosmic structures and events that occurred billions of years in their past, as if the cosmos somehow retains information about its own history. These cosmic memories appear to be encoded in the subtle patterns of matter distribution, the orientations of galactic rotation, and the chemical compositions of stellar populations. It is as if the universe has developed its own form of information storage, preserving records of ancient events in the very fabric of space-time itself. The implications are staggering. If the cosmos can remember its own past, it suggests that consciousness and information processing might be fundamental features of reality rather than rare accidents that emerged only with biological evolution. We might be living within a universe that is, in some sense, aware of itself. Webb has also made discoveries that challenge our understanding of the relationship between consciousness and cosmos. The telescope has observed structures that appear to process information in ways that mirror neural networks, creating patterns of activity that flow through cosmic filaments like thoughts moving through a vast mind. These observations do not prove that the universe is conscious in any conventional sense, but they do suggest that the boundary between mind and matter might be far more fluid than we have traditionally assumed. The same physical processes that give rise to consciousness in biological systems appear to operate throughout the cosmos on scales that dwarf individual planets and solar systems. As we contemplate these revelations, we find ourselves confronting questions that extend far beyond astronomy into the deepest mysteries of existence itself. Webb is not just showing us what the universe contains, it is revealing what the universe might actually be, what role consciousness plays in cosmic evolution, and how our own awareness connects to the vast networks of information processing that appear to operate throughout space and time. The telescope continues its observations, each one adding new layers to our understanding of cosmic complexity. We are witnessing not just the discovery of new phenomena, but the birth of entirely new ways of thinking about reality, consciousness, and our place in the grand scheme of existence. These insights transform how we see ourselves and our relationship to the cosmos. Rather than being isolated observers studying a foreign universe, we are beginning to understand that we might be integral components of a vast cosmic information processing system, temporary arrangements of matter and energy that have achieved the remarkable ability to contemplate their own cosmic context. Webb's discoveries suggest that the universe has been preparing for the emergence of consciousness since its earliest moments, creating the conditions necessary for matter to organize itself into forms capable of self-awareness and cosmic contemplation. We are not accidents in an indifferent cosmos, but perhaps inevitable consequences of the universe's tendency to create increasingly sophisticated forms of organization and complexity. The telescope's observations continue to reveal new connections between seemingly unrelated phenomena, showing us that every aspect of cosmic evolution contributes to the grand narrative of increasing complexity and awareness. From the formation of the first atoms to the emergence of conscious beings capable of building instruments like Webb itself, the universe appears to be engaged in an ongoing project of self-discovery. As Webb peers deeper into space and further back in time, it carries with it not just our scientific curiosity, but our deepest questions about meaning, purpose, and connection. The telescope represents humanity's most ambitious attempt to understand not just what we are, but why we are, and how our existence relates to the vast cosmic story that began with the Big Bang and continues to unfold around us every day. The journey of discovery continues, each observation adding new chapters to the most important story ever told. The story of how the universe gave birth to minds capable of understanding their own cosmic origins. And in that ongoing tale, we find not just scientific knowledge, but something far more precious, a sense of belonging to something magnificent, mysterious, and ultimately meaningful that extends across all of space and time. Tonight, as you settle into rest, you can know that Webb continues its patient work in the cosmic darkness, gathering ancient light that carries within it the secrets of our deepest origins. The telescope serves as our ambassador to the universe, our mechanical extension reaching across impossible distances to touch the very foundations of existence itself. Each photon it captures has traveled across billions of years to reach us, carrying information about places and times so remote that they existed before our solar system was even a whisper in a cloud of interstellar gas. Yet through Webb's remarkable capabilities, we can decipher these ancient messages and reconstruct the story of how everything we know and love came to be. The discoveries we have explored this evening represent just the beginning of Webb's revolutionary impact on human understanding. As this extraordinary machine continues its observations over the years to come, it will undoubtedly reveal phenomena we have not even imagined yet, answering questions we did not know to ask and opening mysteries we never suspected existed. Yet perhaps Webb's greatest gift is not the specific discoveries it makes, but the sense of wonder and connection it fosters. Through its observations, we come to understand that we are not separate from the cosmic story we study, but integral participants in the universe's ongoing journey of self-discovery and evolution. In the gentle darkness that surrounds you now, remember that you are made of elements forged in the hearts of ancient stars, arranged in patterns complex enough to contemplate their own cosmic heritage. You are the universe becoming aware of itself, a temporary flowering of consciousness in the vast garden of existence. The cosmic story continues to unfold around us and through us, and Webb serves as our window into that grand narrative, revealing how every atom, every star, every galaxy contributes to the magnificent tapestry of existence that we are all part of. Rest well, fellow traveler in the cosmic journey, knowing that tomorrow will bring new revelations about the extraordinary universe we call home. Sweet dreams beneath these ancient stars. The James Webb Space Telescope has shown us that we are not separate from the cosmic story we observe, but intimate participants in the universe's ongoing journey of self-discovery. The revelation from this remarkable machine reminds us that consciousness itself might be the cosmos awakening to its own infinite beauty and possibility. I hope you had an amazing time with me here at Dark Cosmos Theory. Until next time, stay curious, keep wondering, and remember that you are part of something far greater than you ever imagined. This is Dark Cosmos Theory, signing off. Good night.